Now let us discuss about the various levels of representation of languages. The languages can be classified into three categories such as high-level languages, assembly languages and low-level or machine languages. High-level languages are the one that are very user-friendly and easily understood by anyone. They can be written in various platforms such as .C, C++, Java, Python, HTML codes, etc. And assembly languages are the one that are made up of mnemonics such as MOV, MVI, add, sub, etc. And the low-level languages are the one that are understood by the machine or the underlying hardware. Now let us discuss how these high-level languages are converted into low-level languages. So this is the levels of representation of languages, high-level languages, and example is .C, .C++, .java files. So these are all the extension of some of the extensions of high-level languages, and these high-level languages are converted into assembly languages which are stored with an extension of .asm with the help of compilers. And this .asm files can be converted into .obj, that is object code files, with the help of assembler. And with this .obj files as input, the linker will convert it into .exe, that is executable file, or .out. Next, this executable files are made up of binary values such as zeros and ones. This binary coded value will alone be understood by the underlying hardware. So this is about general introduction to high-level languages. Now let us see how to write an assembly language program, shortly called as ALP, to add two operand values 32H and 52H, then display the result in the memory location 5200H. H refers to the hexadecimal representation. It means that we are going to add two values 32H and 52H, then display the result in the memory location 5200H. Now let us see how to write this program. Already we have discussed the basic instruction set of 8085. Using those instructions we can write down the program. First we have to take this value. For this purpose you can use the instruction MVI A,32H. It means that the value 32, the immediate data 32 will be copied to the accumulator. Now the content of accumulator is equal to 32. It will be stored in the binary form 0011 0010. Next we have to take the second operand value 52H. For that purpose we can use the same instruction move immediate, but we have to take the next register value, B, and the value we have to copy is 52H. Now this value 52 will be copied to register B. Now the content of B is equal to 52 and it will be stored in the binary form 0101 and for 2 0010. So these are all the contents of register A and register B. Next, the operation that we have to execute is add. So the instruction we can use is add B. It means that this instruction will add the content of accumulator with the specified register B, and the result will be again stored in the accumulator. So this is the function of this instruction. So the values in the binary form will get added. If you add these two values, we get the result as 0, so the value we get is 84H. It will be again stored in accumulator. The last part of the question is to display the result in the memory location 5200H. We have the result in the accumulator and we have to display it in the memory location 520. For this purpose, we can use the instruction store accumulator. So, STA 5200H. It means that the value 84 will be copied to the memory location 5200, which can be displayed to the user. Finally, we have to stop this program. So, the last instruction will be HLT halt. So, this is the instruction to add two immediate data values 52, 32 and to display the result in the specified memory location. So, this is the first sample program. The next sample program is we have to add two values and the values that we should get during the runtime, and again the display the result in some other memory location, let us say 5000, let us say 4500H. We have to, so in the previous example 52 and 32 are immediate data, but in this example we have to get the value during runtime. So for that purpose, again we will start with the instruction. So first we have to decide what are all the inputs that we are going to give. So for this purpose, we have to decide in which memory location we are going to give the two input values. For example, let us say the input values will be given in the memory location 2500. The first input value that we are going to give is 32H, and the second input value we are going to give in the next memory location 2501, it will be 43H. So we have to decide the input memory location. After that you can start doing the program. So the first instruction is you have to use the instruction LDA 2500H. It means that whatever value that we are going to give in this memory location 2500 will be copied to accumulator. So now the value of accumulator will become 32. Next, if you want to load the second value to the accumulator, we are already having the value in accumulator as 32. So we have to copy this 32 to some other register, let us say B. So for that purpose, we can use the instruction MOV move, and from A we have to move to B. So this is the format, move B comma A. It means that the value present in accumulator 32 will be copied to the register B. Now the content of B is equal to 32. A is also 32, B is also 32. The next thing we have to do is we have to load the value 43 to accumulator in order to perform the addition operation. So the same instruction LDA 2501H is performed. It means that the value present in 2501, that is 43, will be copied to accumulator. Now the content of accumulator will change as 4343. Now we got the two operand values in the registers A and B. The next thing we have to do is to perform the addition operation. So that is executed using the instruction add B. So it means that accumulator will be added with the register B and the result will be again stored in the accumulator. So this operation will be performed in the form of binary and the result 75H will be again stored in the accumulator. Then we have to display the result in 4500. So for that purpose, same instruction STA can be used. So STA 4500H. So the value of accumulator will be displayed in the memory location 4500 as 75. Then finally you have to stop this program using HLT instruction. So this is to add two values during runtime. Next, we will discuss about some of the advanced instructions or additional instructions that are not discussed earlier. Additional instructions. We know that the five types of 8085 instruction set are data transfer operations, arithmetic operations, logical operation, branch operations, and the last one is machine control operations. So data transfer, the basic instructions we have discussed is move immediate, LDA, STA, that is load accumulator, store accumulator, in and out. Now we are going to discuss about additional instructions such as LDAX, STAX, LXI and XCHG exchange. Let us see one by one. So the first instruction is LDAX. It means load accumulator indirect. Load accumulator indirect. So the syntax is LDAX followed by B or D register pair. Example is LDAXB, LDAXD. If you execute this instruction, then the content of B and C register will act as a memory location and the operand value or the data value present in that B-C register pair will be copied to accumulator. For example, if the value of B is equal to 30 and if the value of C is equal to 50, then together this value 3050 will be considered as 16-bit address value, and the data value present in this 16-bit address value, let us say 10, this 10 will be copied to accumulator or register A. So this is the function of LDAXB. If you execute this instruction LDAXD, then the content of DE register pair will act as a memory location and the data value present in that memory location will be copied to accumulator. Example, D is equal to 40 and E is equal to 33. Then it refers to the memory location 4033, and if suppose there is a data value such as 5A, this 5A will be copied to register A, that is accumulator as 5A. So this is the function of LDAX instruction. So the next instruction is STAXB or D. It means that store accumulator indirect. The function of this instruction is, if you execute, the function of this instruction is to copy the contents present in accumulator to BC register pair. The function of this instruction is to copy the content of accumulator to the memory location specified by BC register pair. Example is, if B is equal to 20 and C is equal to 50, then it refers to the memory location 2050. If the value of accumulator, if the value present in the accumulator is equal to 2BH, then this 2B will be copied to the memory location 2050. If you execute this instruction STAXD, then the value present in accumulator, this 2B will be copied to the memory location specified by DE register pair. Example is, D is equal to 30 and E is equal to 70, then it points to the memory location 3070. In that 3070, this 2B value will be copied. So this is the function of STAX. Next instruction is LXI. The syntax is LXI followed by a register pair and followed by a 16-bit address value. Example is LXI H, 5070. If you execute this instruction, then this value, then the 16-bit address value will be divided into two parts as higher order address and lower order address. This lower order address will be copied to L register pair and this higher order address value will be copied to H register pair. Another example is LXI B, 3080. If you execute this instruction, then this lower value 80 will be copied to C register and the value 30 will be copied to B register. So this is the function of LXI, that is load register pair immediate. I refers to immediate, load register pair immediate. And the last data transfer instruction is XCHG. It refers to exchange operation, that is exchange the contents of H and L with D and E register pair. Example is, if you execute this exchange, the simple, so it is an implicit, so this is an implicit instruction XCHG. If you execute this one, then automatically if the value of H is equal to 30 and L is equal to 40 and D is equal to 50 and E is equal to 60, all these values will get exchanged. So this is before execution. After execution of exchange, then H is equal to 50, L is equal to 60, then D is equal to 30 and E is equal to 40. Next is the arithmetic instructions. Some of the arithmetic instructions are ADC, that is add with carry, subtract with borrow SBB, then add with carry immediate ACI, subtract with borrow immediate SBI, then DAD double add, then INX increment register pair and DCX decrement register pair. Whenever you encounter this letter X, it means that register pair is involved in the corresponding operation. So these are examples of arithmetic operations. Let us see one by one. So the first arithmetic operation is add with carry, ADC. From the name itself, we can infer that addition operation is going to execute between contents of the accumulator, the given register, and along with the carry bit is also included. So this is the function of ADC operation. Example is, if A content of accumulator is equal to 20H and the content of B is equal to 03H and the carry bit is 01, then all these will be added together. The instruction we have to give is ADC B. If you execute this instruction ADC B, then content of accumulator will be added, then the content of accumulator will be added with register content B and carry bit. So if you add this, you get the value 06H. Again the result will be stored in A. So you can say that A is equal to A plus B plus C. That is content of accumulator, content of register B and content of carry bit. All these will be added and the result will be again stored in accumulator. So this is ADC. So the next instruction is SBB. It means that subtraction with borrow. Example is SBB C. Let us say CY because Next instruction is SBB. It means that subtraction with borrow and followed by the register. Next instruction is SBB, that is subtraction with borrow, and it will be followed by any of the register name. So here we have taken as C. So if the content of accumulator is equal to 0, 8 and the content of C register is equal to 0, 2, and if the carry value is 0, 1, then subtraction will take place between these three values, that is A is equal to A minus C minus carry bit. It means 0, 8 minus 0, 2 minus 0, 1. This is equal to 0, 5H. It will be again stored in the accumulator. As we discussed earlier in the basic subtraction operation, the subtraction will take place in the form of 2's complement. The next instruction is ACI, that is add with carry immediate. As like previous example, the data value will not be present in the data value will not be present in the operand. Instead, it will be given as immediate data. Example is ACI 05H. It means that content of accumulator, let us say 02H, and content of the given immediate data and the content of carry bit, let us say 00H. Carry can be either 0 or 1. It will be added. So A is equal to 02 plus 05 plus 00. You get the value 07. It will be again stored in the accumulator. This is add with carry immediate. And the fourth operation is SBI, that is subtract with borrow immediate. It means that the immediate data will be subtracted. Let us say 02H will be subtracted from the content of accumulator and along with the carry value. Here the borrow refers to the carry bit. In SBB also the borrow refers to the carry bit. So content of accumulator is equal to 08H and the immediate data is equal to 02H and the content of carry bit is equal to 01H. Now the subtraction takes place in the form of 2's complement as A equal to A minus the given immediate data minus the carry bit is equal to 08 minus 02 minus 01, which is equal to 06H. The next operation is DAD. It means double add. Double add refers to, the next instruction is DAD. It is double add. It is followed by B or D register pair. Example is, if you execute the instruction DAD B, then contents of BC register pair will be added with the content of HL register pair by default. Example is, if B is equal to 20 and C is equal to 30, H is equal to 40 and L is equal to 10, these value will be added. So 0, 4, 0, 6. Again this value 60 and 40 will be again stored in B and C register. This is the function of DAD-B. If you execute the instruction DAD-D, then the content of DE register pair will be added with the content of HL register pair and again the result will be stored in the DE register pair. Example is D10, E20, H30, L40. All the values get added and you get the result as 4060. It will be again replaced in the register B. It will be replaced in the register C. This is the function of DAD double add. And the next instruction is, so this is the fifth additional instruction. Next additional instruction is INX. It means that increment register pair. If you execute INX H means INX H, then it increment the content present in the HL register pair. Example is H is equal to 20 and L is equal to 50, then it points to the memory location 2050 and if the content present to 2050 is equal to 05, then it gets incremented by 1 as 06. This is the function of INX. If you execute this instruction INX D, then the content of DE register pair will get incremented by 1. Example, D is equal to 10 and E is equal to 50, then it refers to the memory location 1050, and if the value present in that memory location 1050 is 40, then it is incremented by 1 as 41. And you can use this instruction for BC register pair also, INX B. Then the last additional instruction is DCX, that is decrement register pair by 1. So DCX B, if you execute this instruction, the content present in the BC register pair will be decremented by 1. For example, B is equal to 50 and E is equal to 32. It refers to the memory location 5032, and whatever the data present in this 5032, let us say 06, it will be decremented by 1 as 05. So this is the function of DCX. It can be used for H register pair and also D register pair. So whenever you encounter this X, it means that register pair is involved. Whenever you encounter this I in the instruction, it means that immediate data comes into act. So this is about additional instructions of arithmetic operations. Next we will discuss about additional logical operations. The additional logical operations are RLC, rotate accumulator left, RRC, rotate accumulator right, rotate accumulator left through carry, and rotate accumulator right through carry RAR. All these are 4 types of rotate instructions or rotate operations. We will discuss one by one. The first category is RLC. RLC refers to rotate accumulator left. For example, if the register value now consider this diagrammatic representation of a register. So this is the bit value of the corresponding register, and the bit value starts from D0 to D7, and this is the carry bit. If you execute this instruction RLC, rotate accumulator left, then this D7 will be rotated to the place of D0. So after execution of this instruction, the format of the register content will become here D7, here D0. It will be rotated. So D0, D1, D2, D3, D4, D5 and D6. So this will be the position of the bits after RLC, and carry flag also will contain the value D7 because this D7th bit is rotated. So whatever the value present in MSB will be copied to the carry, and the same bit also copied to so whenever execute this RLC instruction, the most significant bit, that is D7th bit, will be copied to the carry, and also the same bit will be copied to D0, and all other bits are shifted by 1 in this fashion. Next instruction is RRR. The next instruction is RRC, rotate accumulator right. So in this instruction, let us consider the format, general basic format of any register. D0, D1, D2, D3, D4, D5, D6, D7 and the carry bit. So if you execute this instruction, this D0 bit will be stored in the place of D7 and carry flag. So after execution of this instruction, the position of the bits will be D0 will be placed here. Then D1, D2, D3, D4, D5, D6, D7. It means that it will be shifted in this fashion. And it will be placed. And the carry flag also contains the D0 bit value. So this is the position of the bits after RRC. The next instruction is RAL, that is rotate accumulator left through carry. So this is the content of the accumulator register. D0, D1, D2, D3, D4, D5, D6 and D7 and carry is here. Let us say the value of carry is CY. Then this instruction RAL performs rotate operation in such a way that the D7th value will be placed in carry part and this carry value will be stored in the D0 and again the rotation happens in this manner. So after execution, the position of the bits will be here carry flag and here D0, D1, D2, D3, D4, D5 and D6 and in the carry flag D7 will be placed. So this is the position of the bits after execution of this instruction RAL, rotate accumulator through carry. It means that the carry bit is also rotated, involved in the rotation. The last rotation type is RAR, that is rotate accumulator right through carry. We have to perform right rotation including the carry bit. So the contents of the accumulator register are D0, D1, D2, D3, D4, D5, D6, D7, D8 and here it's the carry bit CY. Now the value D0 will be placed in the carry bit value and this carry value will be stored in the place of D7 and all other bits are shifted in this manner. So the corresponding position of the bits after execution of this RAR will be D0, D1, D2, D3, D4, D5, D6, D7 carry flag and here in the carry flag D0 will be stored. So this is the position of the bits after execution of RAR. So these are all the 4 types of rotation operations. And the next logical operation is based on compare operation. The instruction is CPI. It means compare immediate. The example is CPI04H. It means it compares the content of accumulator with the given immediate data. For example, if the content of accumulator is equal to 05H and the given immediate data is 04H, both the values get compared. If the value of accumulator is greater than the given immediate data, then carry flag will be reset. Reset means 0. If the content of accumulator is less than the immediate data, then carry flag will be reset. Then the carry flag will be set. So set means 1 and reset means 0. If suppose A is equal to immediate data, then again carry flag will be reset. So this is the conditions that affect the flag. So this is the condition that affect the status of the carry flag when you execute this CPI, that is compare immediate. So these are all the additional logical operations. Next is the branch operation. In branch operations, we have discussed all the branch operations in the last session itself. So the various types of branch operations are jump operation, then call operation and return operation. It is further classified as conditional jump, unconditional jump, again conditional call, unconditional call, and again conditional return and unconditional return. We have already discussed the unconditional means without any condition the corresponding jump will occur. Unconditional call means without any condition the call will happen, and return means without any condition return will execute. Conditional means based on the status or condition of the flags, corresponding jump, call and return will happen. The main flags are on carry, no carry, 0, jump on 0, jump on parity even, parity odd, positive, minus. So jump on carry, jump on no carry, jump on Z, jump on no 0, jump on parity even, jump on parity odd, jump on positive, jump on minus. Likewise, call if carry, call if no carry, call if 0, call if no 0, call if parity even, call if parity odd, call if positive, call if minus. It means carry flag is equal to 1, carry is equal to 0, Z is equal to 0, Z is equal to 1, Z is equal to 0. It means parity bit is equal to 1. That is, number of ones present in the result should be even, then parity will be set. P is equal to 0, sign flag is equal to 1, sign flag is equal to 0. So here sign flag is equal to 0 and minus means sign flag will be 1. So these are all the various branch call. So these are all the various branch operations. And the last category is machine control operation. The basic machine control operations are HLT and NOP, that is halt and no operation. And the additional machine control operations are EI, enable interrupt, DI, disable interrupt, SIM, set interrupt mask, and RIM, read interrupt mask. These things we will be discussing in the forthcoming interrupt section. So these are all about additional instruction set of 8085. So the additional, let us summarize once again. The additional data transfer instructions are LDAX, STAX, LXI and XCHG exchange. Then the arithmetic operations are ADC, SBB, addition with carry, subtraction with borrow, addition with carry immediate, subtraction with borrow immediate, DAD double add, INX increment register pair, and DCX decrement register pair. And the additional logical operations we have discussed is rotate operations such as RLC, rotate left through RLC, rotate accumulator left, rotate accumulator right, RRC, RAL, rotate accumulator left through carry, and rotate accumulator right through carry, RAR. and the compare instruction CPI, that is compare immediate. And finally we have discussed the branch operations, that are basic operations, jump, call and return. And last, machine control, additional machine control operations are EI, enable interrupt, disable interrupt, then set interrupt mask, and last one, read interrupt mask.